Hi everybody, my name is Nicolas Lepage. I'm a developer at Zenica IT in France. I work mostly with JavaScript and I also like experimenting with Go. This is my first talk in English, so don't be surprised, I'm a little out of practice. Today I am going to talk about deploying a Go HTTP server in your browser. First, you may be wondering why. Why would I want to do that? Well, it could be useful for demonstration purposes. I have this little Go project. It is a command line interface tool, which helps me add a text at the bottom or at the top of a JPEG image. And it also has an HTTP subcommand with a form where I can do the same. Select an image and choose some text to add at the top and the bottom. Then the server sends back the image with the text. Now, I would like to put up a little demonstration page for my project, but I don't want to actually deploy a Go server for this. So that's how I started wondering if we could deploy a Go HTTP server in a browser. Since Go 1.11, running a program written in Go in a browser is possible if you build it to WebAssembly. You get a WebAssembly binary, which can be downloaded and executed by a browser. If you haven't heard about WebAssembly, it uses a portable bytecode format executable by browsers and compiled from higher-level languages such as Rust, C, C++, or Go. Of course, Go code executed in a browser has exactly the same limitations as any JavaScript code executed in the same browser. For example, it will not be able to use the OS package to access the client's file system. So it will also not be able to actually start an HTTP server in the browser. However, when an HTTP request is sent from a web page, there are some cases when it will not actually reach the server. One case is when it is intercepted by a service worker, which usually allows web applications to work offline, for example. Now, I think you are starting to see where I'm going with this. The question is, would it be possible to execute a Go WebAssembly binary in a service worker and use it to handle HTTP requests? Let's find out. A little warning before we go any further. When you are targeting WebAssembly, you have to make sure all the code you are trying to build is compatible. This means, for example, that you cannot rely on C bindings, system dependencies, or a database server. Also, you have to be careful with Go's standard library, which for a large part can be built to WebAssembly, but will actually panic at runtime. That being said, today I'm going to focus on the HTTP side of things. First, let's have a quick look at how it is possible to respond to an HTTP request from a service worker. When a service worker intercepts an HTTP request, it receives a fetch event. The fetch event contains a request object which holds all the information we need about the requests, method, headers, and also the body contents, if any. The fetch event also has a respond with method, which accepts one parameter of type response or promise for a response. So, by reading the request object and building a response object to give to respond with, we are able to respond to an HTTP request from a service worker. However, what we want to do is delegate this task to a Go WebAssembly binary. Now, let's take a step back and review how we usually build an HTTP server in Go. The most straightforward way is to use the HTTP package. First, we define HTTP handlers using handler, which accepts a handler, or handlefunc, which accepts a simple function. Indeed, handlers are simple functions, which receive a response writer and a request. So we can already see that this looks a lot like the ServiceWorker's fetch event. We may also choose to define handlers using some third-party libraries, such as Go WebAssembly. Then, once our handlers are defined, in most cases, we will call listen and serve, which will start listening for HTTP requests and use our handlers to respond to these. In our case, we would like to reuse as much as possible of this code we wrote, but use it to respond to a request intercepted by a service worker. Provided the handlers are WebAssembly compatible, we can keep and reuse them as they are. So this is nice because the handlers are the main part of our code. This is where we declare all the logic. Of course, the one thing we are not going to be able to reuse is the call to listen and serve. But this is okay, because we are going to take a pretty radical shortcut. Usually, when we call listen and serve, it takes care of a lot of things for us under the hood. And for each request, it calls the handler if we gave one in parameter, or default serve.mux, which is the default handler. So what we can actually do is directly call the serve HTTP method of the handler or of default serve.mux. So let's review the plan. Step 1, we intercept the HTTP request in the service worker and send the JavaScript request object to the WebAssembly binary. Step 2, in the WebAssembly binary, we map the JavaScript request into a Go request and call the handler. Step 3, once the handler has returned, we map the Go response into a JavaScript response object and send it back to the service worker. Step 4, in the service worker, we respond to the HTTP request with the JavaScript response object. Now, ideally, we still want to be able to build standard binaries of the server working for Linux or macOS, for example, and also the WebAssembly binary. For this, we can move the listen and serve call into its own file and use build tags to tell the Go compiler that this file is not compatible with WebAssembly. Then we can create a specific file for WebAssembly, this time using the file naming convention instead of the build tags to tell the compiler that this file is compatible only with WebAssembly. And in this file, we are going to use our own API, which will probably look something like this. So a wasmhttp.Serve function, which needs only the handler parameter. Now, let's dive in the implementation of this serve function. If you remember the step 1 of the plan, it needs to receive the JavaScript request objects. So, from the JavaScript point of view, the service worker needs to call the WebAssembly binary with each request object. At the moment, Go WebAssembly binaries have no way to export functions to or other values to JavaScript. So, in order to work around this, the serve function will have to give a callback function to the service worker. The sw.js package allows to create such callback functions using funcOf. FuncOf takes a Go function and creates a JavaScript function from it. The js.value type represents a JavaScript value for Go. The first underscored parameter is the this value of the JavaScript function, which isn't useful for us. The callback function needs only the first argument, which is the JavaScript request object. And it will return one value, which will have to be a JavaScript promise for a JavaScript response object. Then the serve function can register the callback with the service worker by calling a setter function, which has to be previously declared in the service worker's global scope. From the service worker's point of view, we are now able to forward the fetch events request to the WebAssembly binary. In the event handler, we just have to call the Go callback function with the fetch events request. The self variable is a reference to the ServiceWorker's global scope. So this is handy for making the setGo callback function available for the WebAssembly binary. The actual code is a little more complex because we have to use a promise for the callback, otherwise a fetch event might occur before the callback is defined. Step 1 of the plan is done. Now step 2 on the Go side, let's focus on implementing this callback function. We said that this callback function must return a promise for a JavaScript response object. So let's create a new promise and return it. The new promise function I'm using here is not part of the sw.js package. It is a utility function to ease the creation of a new JavaScript promise, which can be a little cumbersome using sw.js. Returning a promise means the callback function is asynchronous. So we need to start a new Go routine. Otherwise, the ServiceWorker would be blocked. And starting a new Go routine actually makes sense, because this is how a Go HTTP server usually works. It starts a new Go routine for each request. And this is it for the callback function. The rest of the work will be done in the new Go routine. Now, the first thing we need to do in this new Go routine is create an instance of a Go HTTP request from the JavaScript request object. We could use the new request function from the HTTP package, but if you read carefully the documentation, it says that this function is suitable only for outgoing requests. But what we actually want is to emulate an incoming request. Thankfully, the HTTP test package has the same new request function for creating requests suitable for passing to an HTTP handler. Usually, this is useful for testing purposes, but this is exactly what we want. So let's use this. The new request function takes 3 parameters. The first 2 are the request method and URL, which we can simply read from the JavaScript request object's properties. The third parameter is going to be a little bit trickier. It is an IO reader for the request body. How are we going to copy the binary data of the request body from JavaScript to Go? Luckily for us, the sw.js package has a copyBytes2Go function just for that. It takes a bytes slice as destination and a reference to a JavaScript typed array of unsigned 8-bit integers as source. So this is okay. With just a few more plumbing, we should be able to copy the body content from JavaScript to Go. We call the array_buffer method of the JavaScript request, which returns a promise from an array buffer. We wait for this promise to be resolved. Then we can wrap the array buffer into an uint8 array. Now we can just create a bytes slice of the same length and finally call copyBytes2Go. A bytes buffer will do just fine for the body parameter of new request. Now we have a Go request. The only important information missing on this request is the headers. Headers are stored in a simple map of strings, both in JavaScript and Go, so we just iterate over these and set each header on the Go request. And the Go request is now complete. We are almost done with step 2 of the plan. Actually, we are already starting step 3. In order to call the handler, we need a value to act as a response writer. For this, we can use the response recorder type from the HTTP test package, which implements response writer and records the response. And now we are able to call the handler's serve.http method. Once the handler returns, the result method of the response recorder allows us to get the HTTP response written by the handler. Now step 2 is really done. Step 3, we need to build a JavaScript response object from the Go response. In fact, the opposite of what we did with the request. In order to build a JavaScript response object, we can use the response constructor, which takes two parameters, the response body and an init object for additional information such as status code and headers. The first parameter accepts several types. One of them is buffer source. Actually, this is not a real type, but either an array buffer or a typed array. Typed array is fine for us. It will allow us to use the copybytes.JS function from the sw.js package, which works just like copybytes.Go, but in the opposite direction. First, we have to read all the response's body content into a byte slice. Then, create a new uint8 array of the same length as the slice, and finally call copybytes.js. In order to build the init object, we can use a map of string to empty interface, which the syscall.js package is able to transform to a new JavaScript object. We only add two values, one for the response status code and one for the headers, for which we can also use a map of string to empty interface. And finally, we can call the response constructor. Back to the Go routine responsible for handling the request, we can finally resolve the promise with the JavaScript response we just built. And we are done with step 3. Now, in the ServiceWorker, we know that the Go callback function returns a promise for a response. For the step 4, we have to send back the response to the page. For that, we can directly give the return value of the Go callback function to the fetchEvents respondWith method. And we are done. Now, the question is, does this actually work? Let's find out with a simple example. The index.html page sends a post request to /API/hello with a JSON body containing a name property. This request should be handled by the API WebAssembly binary, which must return a JSON response with a message property. And this message will be displayed in an alert. On the Go side, we only have one handle func which decodes the request body, then formats a hello message in the response body. And of course, the call to wasmhttp.Serve. We must also add something to block the main Go routine. Here I used an empty select, which is not pretty, but works. Let's try this out. I'm using a private window to avoid having cache or already registered service workers. Okay. We can already see the requests for the page and for the several JavaScript files of the service worker, and a last request for the WebAssembly binary. If we call the API, the alert message is OK, and we can have a look at the request, and we can see that it was handled from the service worker. OK. Now, let's come back to my little project, which was the Catption server. The hello example only uses a server to exchange JSON messages. But this time, the WebAssembly binary will actually serve the HTML page containing the form. So what we can do is create a small HTML file, which will only be responsible for registering the service worker. Once the service worker is activated, it will trigger a reload of the same address, which will now be served from the WebAssembly binary. Let's see if this works. Okay, let's have a look at the requests. We have our first request for the page and several requests for the ServiceWorker files, the WebAssembly binary, and finally, a new request for the page, but this time served from the ServiceWorker. Now let's try to generate an image. Okay, this one, and it generates. Let's go. So this is a little slower than the actual server, but it works fine. And if we have a look at the request, we can see that it was served from the ServiceWorker as well. Okay. So far, in the examples I've been using, the server is stateless. This means it can be stopped and restarted as much as we want. And this is actually a good thing, because the lifecycle of service workers is event-based. The browser will start the service worker only when it is necessary. For example, when a fetch event is received. Then, if no more events are received, after some time, the browser may decide to stop the service worker and kill the WebAssembly binary. So if my server is stateful, the state will be lost. So how can we work around this? Well, there is no real solution here. The service worker specification doesn't allow to keep a service worker alive if it has no clients. This means we need at least one page to be loaded in the scope of the service worker if we want to be able to keep it alive. The most we can do is send periodic messages from the page to the service worker in order to keep the browser from stopping the service worker as long as the page is loaded. In summary, it is not really possible to have a stateful server living in a service worker. More information is available on the GitHub project page, including a usage section to help you do the same with your own project. If you give it a try, please let me know. I will be glad to have your feedback. In conclusion, as you would expect, it is not really possible to deploy a Go HTTP server in a browser. However, it is possible to execute Go HTTP handlers in a service worker. Using build conditions allows to reuse most of the code we usually write for building a Go HTTP server, but targeting WebAssembly requires this code to be compatible. And finally, we saw that deploying a long-running stateful server in a service worker is not a good idea because of the life cycle of service workers. Thank you for listening. Thank you to FOSDEM organizers and to the Go Dev Room organizers. And a big thank you to all those who helped me prepare this talk.